Hello and welcome back to Fireside Chats with Mr. Bacallier, where we talk about math and enlighten people's lives. Today, we're going to be talking about L'Hôpital's rule, which is spelled sort of funny because it's French, and things from France are funny. L'Hôpital's rule is spelled this way. And it looks like it says La Hospital, but it was originally L'Hôpital's rule, which has a little hat here, which is sort of fun.
Wait,
and
where is the rule, Dad?
Oh, I didn't write rule, Alexis. So either of these you could then follow with rule. It's really nice to do these lessons when you have commentary. Alexis, can you see the whole whiteboard in the screen? Okay, perfect. So L'Hôpital's rule is a special way to find a limit of a function. So we've dealt with functions before where it's hard to find their limits. These could be as simple as something that said the limit as x approaches 3 of x squared minus 9 over x minus 3. And you'll recall that when we graphed this before, we found the limit before, we'd factor this out to x plus 3 times x minus 3 over x minus 3. And we would find that we would have a hole at x minus 3, or at the 0 that's created by x minus 3, which means that there's going to be a limit at the value x equals 3. This would end up looking like a little graph that went through the value 3 and went like this. And at the value 3, we'd have a hole. At this point, the limit exists. But we can't find the limit by plugging in 3, because if we plug in 3, we would end up with 3 squared, which is 9 minus 9, over 3 minus 3, which is 0 over 0. And so we would have to figure out other ways to find the limit. Well, L'Hôpital's rule that fixes that, which is fantastic. It makes finding some of these terrible limits a lot easier. And what L'Hôpital's rule tells us is that if we know that the limit as x approaches some value a of f of x is equal to the limit as x approaches a for some other function, let's call it g of x, and if these things are equal to 0 or infinity, then, oh wait, not done yet, and the limit as x approaches a of f prime of x over g prime of x exists, that's important, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. And that's a whole lot of writing that looks really confusing. Doesn't it look confusing, Alexis? Alexis is nodding her head. She agrees that it looks confusing. So all of this probably doesn't make any sense to you. But, hi Poppy, but this is the basis for L'Hôpital's rule. And L'Hôpital's rule is going to help us to find the derivative of something that looks like the limit as x approaches 3 of x squared minus 9 over x minus 3. Now, this bit right here is important. This bit is what's going to create something called the indeterminate form. And in our case, in AP Calculus, the indeterminate forms that we are going to be particularly interested in are going to be the forms 0 over 0 or infinity over infinity. And if we find either of these two indeterminate forms, and there are other indeterminate forms, these are just the ones we're interested in right now, then we're going to use L'Hôpital's rule. So let's go back to that example that we were talking about originally. The limit as x approaches 3 of x squared minus 9 over x minus 3. If I plug in 3 into this thing, I end up with 0 over 0, which is an indeterminate form. Finding this means I can use L'Hopital's rule. And I will say that on the AP test, if you're doing this on a free response question, you want to first actually show that you're getting an indeterminate form. If you don't show this, then you haven't verified that you know the conditions for being able to use L'Hopital's rule. So now that I have 0 over 0, I'm going to take the derivative of the numerator and the denominator. So the derivative of the numerator is just going to be 2x, and the derivative of the denominator is going to be 1. And what L'Hopital's rule tells me is that if the derivative of this becomes the indeterminate form, and the limit as x approaches a, which in this case is 3, of this thing exists, then this limit is equal to this limit. Well, that's fantastic, because this limit is easy to find. We can just plug in 3, and we get 6. And that's our answer. And if we were to have gone back through and graphed this function originally, as I did right at the beginning of this problem, we would have had a function with a slope of 1. It came up, and at 3, it would have had a hole, and then kept on going. So that point is where we wouldn't have our function, but we'd still have a limit. So L'Hopital's rule helped us find the limit. Let's look at some other examples of places where we can do this. So we could take the limit as x approaches 0 of tangent of x over x. If I plug in 0 into tangent, remember that tangent is my y value divided by my x value on the unit circle. Tangent of 0 is going to be 0, and plugging in 0 here is going to give me 0. So that means that this thing comes out to the indeterminate form, which means I can use L'Hopital's rule. The derivative of tangent is going to be secant squared of x, and the derivative of x is going to be 1. So now I'm going to evaluate secant squared at 0. Well, secant, remember, is the reciprocal of cosine, and the cosine of 0 is 1, which means that the secant of 0 is 1, and so the secant squared of 0 is also 1. And so we end up with 1 over 1. And so my final answer is 1. L'Hopital's rule is fantastic. Sort of makes you wonder why I made you calculate all of those limits earlier on in the year when I didn't let you use L'Hopital's rule. Because sometimes L'Hopital's rule doesn't work, which we'll get to in a minute. Now, let's say that we have limit as x approaches -2 of x cubed plus 8 divided by x squared minus 4. Let's try first evaluating a limit, because we always try evaluating a limit by plugging in numbers. If we plug in -2, we would end up with -8 plus 8 divided by 4 minus 4, which is going to be 0 over 0, which once again gives us the indeterminate form. Remember, we're looking for either 0 over 0 or infinity over infinity. Because we got the indeterminate form, we can use L'Hopital's rule. We take the derivative of this, which will be 3x squared. We take the derivative of this, which will be 2x. Now we plug in -2 again. We're going to find the limit as x approaches -2 of this thing. That's going to be 3 multiplied by 4, which is going to be 12, divided by 2 times -2, which is going to be -4. And so my limit is going to be -3. Let's look at some problems that get a little bit nastier. So let's say that we had the limit as x approaches infinity, which we're allowed to use it for x approaching infinity as well as x approaching some other number, of x cubed minus 4x squared plus 7 divided by 3 minus 6x minus 2x cubed. So let's think about what we know about these functions. This is a cubic function that's positive. Cubic function that's positive is going to start low and high. And so the limit as x approaches infinity of this thing is going to be infinity. This is a negative cubic function. A negative cubic function is going to start high, it's going to end low, which means that we get negative infinity. So we have another one of those indeterminate rules that or indeterminate forms that we've been looking for. We have infinity over negative infinity. So if we take the derivative of these two things, we're going to get 3x squared minus 8x divided by negative 6 minus 6x squared. So the limit of this should equal the limit of this. Well, let's evaluate what the limit as x approaches infinity of this thing is going to be. 3x squared is a positive quadratic, so it's going to look like this, which means as x approaches infinity, this thing is going towards infinity. And as x approaches infinity in this thing, this is a negative quadratic, this is going to approach negative infinity. So we now know that the limit of this thing should equal the limit of this thing, but we don't know what the limit of this thing is because we got a second indeterminate form. So we use L'Hopital's rule again. The limit of this thing should equal, this is going to be 6x to the first power minus 8 divided by, down in the denominator, we're going to have negative 12x, like that. Now, if I plug in infinity into this thing, this would go onward towards positive infinity. This thing would go down towards negative infinity. And once again, I have infinity divided by negative infinity. So let's do it again. And I end up with 6 over negative 12, the limit as x approaches infinity of 6 over negative 12. Well, what is this thing going closer to? This thing is going closer and closer to negative 1/2. And that is my limit. Now, L'Hopital's rule will not always work. So don't just assume, oh, I need to find a limit, I'm going to use L'Hopital's rule. You could have something that looks like this, which is a problem that sometimes they like to give you to trick you. You have the limit as x approaches 2 of x cubed plus 8 divided by x squared plus 4. Remember, before we did this with x squared minus 4. If I plug in 2 cubed plus 8 is going to be 16. 2 squared plus 4 is going to be 8. This is just a straightforward limit of 2. I don't need to use L'Hopital's rule. I don't have the indeterminate form, so I can't use L'Hopital's rule. If I had used L'Hopital's rule, I would have had 3x squared divided by 2x. And if I had plugged 2 into that thing, I would have gotten 4 times 3 is 12, divided by 2 times 2 is 4, which would be 3, which is not the value that I'm looking for. So don't assume that you can always use L'Hopital's rule. Again, in order to use L'Hopital's rule, you first have to show that you get one of those indeterminate forms that we talked about before. Hopefully this gives people at least something to start off with using this rule, and you can move forward from there with anything that you need to do with limits. Have a wonderful day, and I'll talk to you all soon. Bye.